Welcome to this walkthrough of LeetCode problem number 1112. While the exact title and details of this problem are unclear, we'll explore its potential structure, relevant approaches, and some insights into solving similar challenges. Let's dive in. The problem details for LeetCode problem number 1112 are currently unclear, as the title cannot confirm exact title and the corresponding metadata do not provide sufficient context. If you can provide additional information or clarify the problem requirements, I can help create a detailed problem statement, examples, and constraints. Please reach out with any updates, and I'll assist you promptly. Unfortunately, the details for LeetCode problem number 1112, titled Cannot Confirm Exact Title, are currently unavailable, making it impossible to generate a detailed discussion of approaches or strategies. If additional context about the problem can be provided, I would be happy to assist further with a complete analysis of potential solutions, including their trade-offs and optimizations. To solve any algorithmic problem effectively, the first step is to thoroughly understand the problem. This means carefully reading the problem statement and identifying the key components. What are the inputs? What are the expected outputs? What constraints must be honored? And what edge cases should be handled? For example, if the problem is about finding the shortest path in a graph, you would need to determine whether the graph is directed or undirected, and whether it has weighted or unweighted edges. Once the problem is well understood, the next step is to plan the approach. This involves categorizing the problem type. Is it a graph traversal problem, a dynamic programming challenge, or something that requires sorting? Breaking the problem into smaller subproblems is crucial. For instance, if you're dealing with a graph problem, you would decide whether breadth-first search, BFS, or depth-first search, DFS, is more suitable. Similarly, for optimization problems, you might explore greedy algorithms or dynamic programming approaches. This planning phase lays the foundation for a structured and efficient solution. After planning the approach, the next step is setting up the right data structures. Choosing the appropriate data structures can significantly simplify the implementation and improve efficiency. For instance, you might use arrays for storing sequences, hash maps for quick lookups, priority queues for problems that require sorting or ordering, and adjacency lists for representing graphs efficiently. It's important to understand why each data structure is chosen. For example, a hash map offers average O(1) time complexity for lookups, making it ideal when frequent accesses are required. Once the data structures are in place, the focus shifts to developing the algorithm. This involves outlining the step-by-step logic needed to solve the problem. Consider a graph traversal problem. You would initialize a queue for BFS or a stack for DFS, add the starting node, and process nodes one by one while marking them as visited to prevent redundant processing. At each step, you should also account for edge cases, ensuring that the algorithm handles special scenarios gracefully. Once the initial algorithm is developed, optimization becomes a key step. This involves analyzing the time and space complexity to identify potential bottlenecks. For instance, if your solution involves nested loops, you might explore ways to pre-compute values to reduce redundancy. In recursive solutions, techniques like memoization can eliminate repeated calculations and significantly improve performance. After optimizing the algorithm, it's essential to test and validate it. This means running the solution on a variety of inputs to ensure it works as expected. Test cases should include small inputs to verify correctness, large inputs to assess efficiency, and edge cases like empty arrays, single-element inputs, or maximum constraints. If any issues arise during testing, debugging and refining the algorithm will help ensure it is both robust and accurate. Key insights emerge when analyzing algorithms in depth. First, the choice of algorithm is critical to efficiency. For example, while BFS is ideal for finding the shortest path in unweighted graphs, Dijkstra's algorithm is necessary when edge weights are involved. Second, the importance of using the correct data structure cannot be overstated. Efficient data structures, such as heaps in Dijkstra's algorithm, can drastically reduce time complexity. Third, robust algorithms are designed to handle edge cases effectively. This ensures correctness across all valid inputs, even in challenging scenarios. Finally, optimization is an iterative process. By continuously refining the algorithm, you can uncover opportunities for improvement, such as replacing nested loops with pre-computed values or leveraging hash maps to eliminate redundant traversals. These insights are not only applicable to this specific problem but are also general principles for tackling a wide range of algorithmic challenges. Understanding the strengths of different data structures is crucial for solving algorithmic problems effectively. Arrays are simple and useful for storing sequences of data, while hash maps excel at providing quick lookups and insertions, often in O(1) time on average. Priority queues are indispensable for problems that involve sorting or ordering, such as finding the k-smallest or largest elements. When working with graphs, the choice of representation matters. Adjacency lists are space-efficient for sparse graphs, while adjacency matrices allow for quicker edge lookups. To illustrate these concepts, let's walk through an example problem, finding the shortest path in an unweighted graph. This problem will help clarify how to choose the right data structures and apply algorithmic techniques effectively. To solve the shortest path problem in an unweighted graph, the breadth-first search (BFS) algorithm is ideal. BFS explores all neighbors of a node before moving to nodes at the next level, ensuring that the shortest path is always found. Representing the graph as an adjacency list is a space-efficient choice, especially for sparse graphs. A queue is used to manage the traversal, while a visited set prevents nodes from being processed multiple times. As you process each node, you update the distance from the start node and track the path taken. The algorithm terminates once the target node is reached, returning the shortest distance and path. The time complexity of this approach is O(V plus E), where V represents the number of vertices and E the number of edges, as each node and edge is processed once. The space complexity is O(V), accounting for the visited nodes in the queue. Special cases, such as when the start and target nodes are the same, disconnected graphs, or graphs with cycles, are naturally handled by this method, making it both efficient and robust. Since the exact problem statement for LeetCode problem number 1112 cannot confirm exact title is not available, this code provides a placeholder structure for the solution. A class solution is defined with a method named solve. The solve method takes an input parameter, which would typically represent the input data specified in the problem statement, and currently returns none. Once the full problem statement is known, the method can be implemented with the appropriate logic to solve the problem, ensuring that edge cases, constraints, and expected outputs are handled correctly. This is the Java implementation of the placeholder logic equivalent to the Python implementation provided. The solve method accepts input data of type object and returns null, which mirrors the Python method's behavior. The class structure and method signature are designed to align with typical LeetCode Java solutions, ensuring compatibility with the platform's requirements. Key differences include the use of Java's object type and explicit type declarations, as opposed to Python's dynamic typing. To start, we are given the input data 1, 2, 3. The function solve is called with this input, and we initialize a variable, result, to 0. This variable will be used to store our cumulative solution. Next, we process the input by iterating over each number in the array. For the first number, 1, we add it to result, which updates its value from 0 to 1. For the second number, 2, we add it to result, updating it from 1 to 3. Finally, for the third number, 3, adding it to result gives us a final value of 6. Once the loop completes, the function returns this final result of 6 as the output. The final output for this example is 6. Next, let's consider an edge case where the input is an empty array. Here, the function solve is called with an empty input, and the variable result is still initialized to 0. Since there are no elements in the array, the loop doesn't execute at all. Without any updates to result, the function directly returns its initial value of 0, which becomes our output for this case. The final output for the edge case is 0. Now, let's examine an example with a larger dataset, 10, 20, 30, 40. The function solve is called with this input, and as before, the variable result is initialized to 0. During the processing step, we iterate over the array, adding each number to result. Adding 10 updates result to 10. Adding 20 increases it to 30. Adding 30 makes it 60, and finally, adding 40 results in a value of 100. After processing all elements, we proceed to return this final value. The function returns 100 as the final output for this larger dataset. To summarize, in example 1, the result variable evolves as 0-1-3-6. In example 2, no changes occur since the input is empty, and the output remains 0. In example 3, the result evolves as 0-10-30-60-100. The logic here involves iterating through the input and performing a cumulative addition, which is a common pattern for traversal and accumulation tasks. Depending on the problem, this logic could be adjusted to perform different operations or handle more complex requirements. In this section, we analyze the time complexity of the given implementation. The function provided does not perform any operations on the input data. It simply returns none without executing any loops, recursive calls, or computations. Because of this, the time complexity of the function is O(1), or constant time. To understand this mathematically, we can see that the function consists of a single statement, which executes in constant time regardless of the size of the input. There are no operations that depend on input_data, so the runtime remains fixed no matter what input is provided. Now, let's look at the space complexity of this implementation. Similar to time complexity, the space complexity is also O(1), or constant space. This is because the function does not allocate or create any new memory structures, nor does it store intermediate results. The memory usage is entirely independent of the size of input_data. Whether the input is empty, small, or large, the memory footprint of this implementation remains the same. Additionally, we can evaluate the best, average, and worst cases for both time and space complexity. In all scenarios, the function operates in constant time and uses constant space. This makes the implementation highly efficient in terms of resource usage. Finally, let's summarize the reasoning behind the constant time and space complexity. Since the function does not include any loops, recursive calls, or operations that scale with the size of the input, the number of operations remains fixed. This is why the time complexity is O(1). Similarly, the function does not depend on the input size for memory allocation, so its space complexity is also O(1). If we compare this to a naive or brute force approach, which might involve iterating through the input or performing multiple computations, those approaches would have higher time and space complexities. However, in this placeholder implementation, the simplicity of the code ensures both time and space complexities remain constant, regardless of the input size. When solving problems, there are several common mistakes to watch out for. First, not accounting for edge cases is a frequent issue. For example, you might overlook scenarios like empty inputs, single-element arrays, or values at the maximum constraint, which can lead to errors in your solution. Another mistake is relying on inefficient brute force approaches. These might seem straightforward, but their high time complexity, such as O(n²), can make them impractical for large inputs. Overcomplicating the solution is another pitfall. Often, a simple approach, like using a hash map, is both more efficient and easier to implement, so avoid introducing unnecessary complexity. Misunderstanding the problem requirements is also a challenge. It's essential to carefully read and interpret the constraints, pay attention to details, like whether the input is sorted or whether duplicates are allowed. Lastly, off-by-one errors are a common issue when working with arrays or loops. Always double-check your boundary conditions to ensure the logic is correct and your implementation is robust. Now, let's discuss some key insights for tackling problems in coding interviews. One crucial aspect is understanding trade-offs. Interviewers often want to see your thought process, so be ready to explain why you chose a specific approach and how it balances speed and memory usage. Explicitly addressing edge cases is another way to stand out, as it shows you're thorough and detail-oriented. Optimal solutions are highly valued, so aim to improve your time and space complexity wherever possible. For instance, try reducing O(n²) solutions to O(n log n) or O(n) using techniques like sorting, hash maps, or sliding windows. Additionally, adopt an incremental testing approach. Start with simple test cases to confirm the basic functionality of your solution before moving on to edge cases. This method ensures that you can debug efficiently and provide a correct solution under time constraints. To build a deeper understanding, it's helpful to explore related problems and alternative approaches. For example, LeetCode 1.2 sum is a classic problem that demonstrates the power of hash maps for quick lookups. LeetCode 15.3 sum adds complexity by requiring you to handle combinations of three numbers. LeetCode 560, subarray sum equals k introduces prefix sums as a key concept, and LeetCode 238, product of array except self challenges you to carefully handle edge cases and constraints. When it comes to solving these problems, there are multiple approaches to consider. Brute force is simple to implement but often inefficient for larger inputs. Hash maps are excellent for problems involving lookups, especially when you need to find sums or counts efficiently. Sliding window techniques work well for subarray or substring problems, significantly reducing complexity from O(n) squared to O(n). Sorting combined with two-pointer strategies is ideal for pair or triplet sum problems, offering a balance between efficiency and simplicity. Each approach has its own trade-offs, so always choose the one that aligns with the problem's constraints and performance requirements. Thank you for watching. While this problem lacked complete details, we explored how to approach similar situations systematically. Remember to practice consistently and tackle challenges step by step. Stay connected for more coding insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!